In this video, we're going to have a new way to think about matrices. So far, we've looked at system of equations, and we had an augmented matrix and a coefficient matrix corresponding to the system of equations. Here's the coefficient matrix, and now we're going to think about a matrix all on its own, as its own mathematical object. Doesn't necessarily have to relate to a system of equations. And we'll define some operations on this mathematical object, these matrices that we will be working with. The first operation will be adding matrices. So if you have two matrices of the same size, then we can add these two matrices together by adding the corresponding entries. So that's how we define matrix addition. Check it out. The third resulting matrix has the corresponding entries added together. Now, to add matrices, we have to have the matrices be the same size. If they're not the same size, then the matrix addition is just not defined. We can scale matrices. So here's an example of multiplying a matrix by 3. And what we do, or what we really define it to be, is scale each element in the matrix by 3. And so this is what we would get by our definition of scaling a matrix. Now, a more complicated operation we can define is a matrix times a column vector. A column vector is just a matrix with one column. So here's an example. Matrix times a column vector. We'd call the matrix A and the column vector X. And the way we define that is we scale the columns of A using the entries in X, and then we add them up. Right? So we scale the first column by 5, the second column of A by 3, and then what we do is we'll scale them, and then we add them up to get a resulting vector that has 4 entries, 4 elements in that resulting vector from this matrix times the column vector. Another example, here's another matrix times a column vector, and we scale the columns of our matrix by 3, 0, and 2, so by the elements in our column vector, and we scale them, and then we add them up, right, to get 13, 10. Now this would be a good spot to stop and think through the way we defined matrix times a column vector, because we'll be using this a lot throughout the rest of the course. And a good thing to think about too is, what does the size of A in relation to X need to be for this to be defined? So stop and think about that. And the answer is the number of columns in A needs to equal the number of elements in X, right? Because we need the number of elements in X to match the columns of A so we can actually scale and add them up, right? We need that to be equal. And then you can think about the resulting size. The result of A times X, well, the size of the result will be the same number of rows in A for the number of rows in our result, and the number of columns will always just be 1. You'll just have one column for a matrix times a column vector. You can also think about what the size of our result will always be. Well, since we're scaling and adding up columns, we'll get a column vector as our result. And the number of elements in that column vector would match the number of rows in our matrix A, right? Because we're scaling and adding up the columns of A. So that would be the size of the result. So it'd be always a good mental check after you've done a computation to see, does the size even make sense? Or you can always ask before you even do the computation, is this matrix times column vector even make sense? Is it actually defined? And if so, then you can scale and add up the columns of A to get your result. Now we'll look at the definition of a matrix multiplied by a matrix. So the second matrix doesn't have to be a matrix with one column, like we just looked at, but it could be more general. So this is how we define a matrix times a matrix. Let A be an m by n matrix, so that's m rows and n columns, and B an n by p matrix, so n rows and p columns. And we'll see why those sizes are like that later. Let the columns of B be expressed as B1, B2, all the way to BP. Right? So there's P columns. This means B can be expressed as B1, B2, all the way to BP inside of those square brackets. So for example, the third column of B is B3. Then A times B is defined as this matrix where the columns are AB1, AB2, AB3, all the way to ABN. So for example, the second column of our result from this multiplication, the second column would be A times B2. So A times B2 would be a matrix times a column vector, like we just looked at. So essentially what we're doing is n matrix times column vectors. Or in other words, n matrix vector multiplications. So let's look at an example. Here's a matrix multiplied by a matrix. So the definition says, do A times the first column of B, then the second column of B, then the third column of B, then the fourth column of B. And those would form the new columns of our result. So here's A times B1. And this is a matrix times a column vector like we just looked at a minute ago. And here's A times B2, A times B3, A times B4. Right, to get each one of these multiplication, to get each one of these computations, right, these matrix times column vectors, right, we just looked at, we scale and add up the columns of the matrix using the elements in our column vector. Okay, so we did those 4 matrix vector multiplications, and those form the columns of our resulting matrix. That is A times B. Now let's think about the sizes of these matrices. So here are the sizes. And notice the resulting matrix, right, A times B, has size 3 by 4. And that's the outer numbers from A being multiplied by B, right? Because we had a 3 by 2 multiplied by a 2 by 4. So the resulting size will always be those outer numbers, 3 by 4. Now this would be a good spot to stop and reflect why this is the case. So think about, why is the size of the result of A times B always those outer numbers? It would always be, the resulting size would always be M by P based on the letters given in our definition. Well, the reason is we're doing n matrix vector multiplications to get our columns of our result. Right? And a matrix times a vector just gives us another vector. We're doing that n times, so we get n columns in our matrix. So in this case, we did 4 matrix vector multiplications, so we get 4 columns for our result. Now, why is there 3 rows? Well, because each matrix times a vector is scaling and adding up the columns of our matrix A, which has 3 rows. Right, so each column in A has 3 entries. So when you scale and add them up, you get 3 entries. So that explains why there's 3 rows in our result. And why also there's 4 columns, because you're doing 4 matrix vector multiplications. Another good thing to stop and think about is, what must be required to even be able to do matrix-matrix multiplication? Well, the inner numbers must match. Right? For this example, we have a 3 by 2 multiplied by a 2 by 4. So notice that they both have the number 2 on the inside. Right? So the inner numbers have to match for the multiplication actually to be defined. Why must that be true? Well, because the definition says we're doing A times B1, A times B2 to get the columns of our result. And so A times B1, it's a matrix times a vector, and we already showed that to do matrix times a vector, you need to have the same number of entries in our vector as the number of columns in our matrix. So the number of entries in the columns of B need to be the same as the number of columns in A, which means the number of rows in B need to be the same as the number of columns in A. And that's why those inner numbers must match. Now that we defined these operations on the matrices, we can talk about the properties that these operations have. So if A is an M by N matrix and B and C have sizes that actually make sense for the operations, Then property A is saying, well, you can multiply B times C and then do A times B times C. Or you can do A times B first and then multiply by C. So either way works. They're equivalent, just like it works with regular numbers, right? It also works with matrices. You can also distribute, and we call that distributing on the left for property B, and also on the right for property C. So distribution still holds true with matrices. And property D, if R is a scalar multiple, it doesn't matter if you do A times B first and then scale it by R, or scale A by R first, or scale B times R, scale B by R first. Either way, it all is the same thing, just like with regular numbers. You can also do that with matrices and a scalar multiple R. Now there's 3 warnings when you're operating with matrices. There's 3 properties with regular numbers that do not hold true for matrix times a matrix. And the first one is A times B is not the same as B times A in general. I mean, maybe there's a particular case where it's true, but in general, A times B is not the same as B times A. If you flip-flop the order of multiplication, then it's you get different things. Warning number 2, the cancellation law does not hold for matrix multiplication. So if A times B equals A times C, it doesn't necessarily mean B is equal to C. You can't cancel the A's on the left, right? It holds true for regular numbers. So like 5 times B equaling 5 times C would mean B and C are the same, but not true for matrices. And warning number 3, if a product A times B is the zero matrix, you cannot conclude in general that either A is a zero matrix or B is the zero matrix. Right? With regular numbers, you could, if A and B were numbers and A times B equaling 0, you could conclude that either A or B was 0, but not so with matrices. Let me show you an example for each warning. So the first one, if you have A times B as shown, you get 23, negative 10, negative 9, 15. And it'd be good practice for you to work out to see if you understand matrix times matrix. But if you flip-flop the order, if you do B times A, then you get a totally different matrix. Warning number 2. If A times B is equal to A times C, right, so there's an example where B and C are different, but A is the same. Even though that A times B gives you some matrix that's also equal to A times C, and you can compute what those are, we see here that B and C are not the same. So you can't just cancel the A's because B is not equal to C. So that is an example of warning number 2. And warning number 3, right, here's 2 matrices multiplied together. That gives you the zero matrix, but notice A and B. And warning number 3, here's 2 matrices multiplied together. That gives you the zero matrix, but notice neither A or B is the zero matrix. Right? So you can have 2 non-zero matrices multiplied together. That gives you 0. The last thing we'll look at are matrices with names. So the zero matrix is a matrix with all zeros as its elements. There's 3 examples. Diagonal matrix, this has any numbers on the main diagonal, which I've highlighted there, and zeros everywhere else. And a diagonal matrix has to be a square matrix of any size, so n by n, so like 10 by 10, as long as there's zeros everywhere except for the main diagonal. The main diagonal could have zeros, but it doesn't have to be. A, B can be any number in the first matrix, and A, B, and C could be any number for that 3 by 3 matrix. And lastly, the identity matrix is a diagonal matrix where the diagonal entries have value of 1. That's what we mean by an identity matrix. Why do we call it an identity matrix? Well, if you consider taking an identity matrix and multiplying it by an arbitrary vector, x1, x2, remember, how do we do that? We'll scale and add up the columns of our matrix. You just get x1, x2. So if you do the identity matrix times a vector, you just get the same vector back. right? The vector that you get is identical to the original vector that you multiplied by. So they're identical. That's why we call it the identity matrix. Likewise, for a 3x3 identity matrix, right, do the matrix times the vector, and you get back x1, x2, x3. It's the identical vector that you get as a result as what you multiplied by. So in general, if we call the identity matrix I times x is equal to x. All right, well, that's it for this video. Thank you.